Okay, so just another word about these non-perturbative things, right? So what these indices mean here is basically, right? We have here like all kinds of particle scattering, right? Like gluons, quark to gluons, like all channels will contribute. And here, what these indices basically just mean is that we take the gluon or a quark out of the proton, one of them, then another quark or gluon, say up, down, strange, charm, whatever, right? It's just sum over all possibilities. So I forgot here sum out of the proton. Then they have a scattering from the two initial partons to the final state parton, and then that fragments into the hadron. And so here should be a sum, over A, B, C, over all possible channels. And these non-perturbative things, right? We basically fit them to data, right? You parameterize the dependence here on say the momentum fraction x a, momentum fraction xb, momentum fraction z. That's from going from parton to hadron. You parameterize all these functions, and then you fit them to data, right? So you basically what you want to get, right? What you want to get at are these functions here, right? They extract it from data from different reference processes, have some uncertainty, right? If you have more precise data, you can beat down the uncertainties and make better predictions, right? That's generally how it works. And that's basically the story, right, for hadron production. So the new component, right, that I want to discuss, that's the very natural extension, right, is like this function here. Right? If you want to talk about anything with jets, we need to understand this function. And so we already know the PDFs, right? So we know them quite well. So what we need is this function here, right? Of course, in the end, we can also use jet data to better constrain this, right? We can sort of turn it around later. But what I want to discuss here is this function. And also, like if you want to do additional measurements, right? If you want to later talk about jet substructure, right? Then what we're going to do is we're still going to start with this basically, right? So if I want to not only know what's momentum and the distribution of jets in terms of angle, right? I'm still going to measure the rapidity and the transverse momentum of the two jets. And then I add like maybe an additional observable here, right? For example, I want to know what is like the mass of these jets, right? Or what is the hadron distribution of the jets or whatever, right? Like I can come up with all kinds of additional observables, but I'm always going to start with this, right? I'm always going to measure just first the jet, and then I measure like additional variables about the jets, right? So I'll always start with that kind of structure, right? Like no matter what observable I'm going to be looking at. Okay, so I'll say more about how to calculate that particular function, but let's first just look at the result. All right, so what you can see here, so again I have this factorization from the previous slide, right? And now we can perturbatively calculate this function, okay? And so, well, that's the result, that's the numerical result. This is not fitted to data, right? You can just directly do a first principles calculation. And so what you see here is the example for a gluon jet function plotted as a momentum fraction z, right? So this is the longitudinal momentum fraction. So how much energy is contained in the jet relative to the initial parton, right? We have a quark or a gluon that fragments, and it fragments in an inclusive way, right? So it produces multiple jets, right? We start with a gluon. It will produce one jet that's the most energetic one, then maybe a second and a third jet, right? Because it emits several gluons, right? And we'll measure all of them, right? So that's sort of the inclusiveness, right, that I was trying to show before, right? Like any jet that comes out, right? That's what this was, right? So if I basically take all the jets, right? I start with a gluon and I get a bunch of jets, and that's not the same number in every event, but I put all of those in histograms, right? And then I get this spectrum here. And so this spectrum, like maybe the most important feature of this is that it has a peak here at very large values of z, right? And that basically means that it's very likely, right, that I find a leading jet that contains almost all the energy, right? The peaks here say, I don't know, even above 0.9, right? So that means for every gluon that I produce in a hard scattering, it's very likely that I'll find a leading jet that has almost all the energy of that initial gluon. Okay, that's the interpretation of this peak. And that's, that's of course very different, right? Like if you look again at the fragmentation function before here on the, the lower right, that was the fragmentation function for a hadron that comes from an initial gluon. And you can see it's very unlikely that you find a hadron that carries all the energy that was initially available, right? It falls off steeply towards 1 versus this jet function peaks at 1, right? And that's basically sort of the difference, right? The reason that we have this close analogy, right, in these polar plots before Pythia, between quarks and jets versus for hadrons, we get this distribution. That's exactly because of these different fragmentation patterns. So how a gluon turns into a hadron and how a gluon turns into a jet is completely different. And the main difference is that jets have a peak at large values of z, and hadrons have fall off very steeply, basically 0 at 1, right? That's the main difference. I mean, of course, this intuitively makes sense, right? Because if you group a bunch of particles together, right? So it's much more likely that they actually contain all the energy that was initially available, versus that's very unlikely to happen for a hadron. Okay, does that kind of make sense? You guys seen these kind of fragmentation functions before? Yes.
So then this plot is the gluon momentum fraction, but then would we see something similar for an arbitrary hadron production with a single quark?
You mean for a different hadron, or for so here you have to basically specify the hadron, right? So this is for a pion. Here this is insensitive for that, right? You just take all the hadrons, like you don't specifically ask for a particular hadron. Now we can of course ask the question, what does it look like for a quark? I don't have the plot here, but it actually peaks even closer to 1. So this distribution will peak, even more sharply at 1. And the reason is basically just that the color factors are different, right? In one case, I have a color factor Ca, which is 3. If I emit a gluon off a gluon, right, it's much more likely to split into 2. Whereas if I have a quark, it's a color factor Cf, which is about 1. It's much smaller was much less likely to happen to split into 2 than for a gluon. And that basically means that the quark jet function will peak even more closely to 1. So this connection between quarks and jets is even better than it is for gluons. They just generally shower more, they're more broad, and not everything will be captured in the jet for gluon. But it's still even you have a very good peak. Yeah, good point. Any other question? So then what maybe I can ask you guys, so what's the peak here on the left? What's happening here? Any thoughts? So this is the leading jet, right? So momentum fraction of leading jet close to 1. Right? It's like one jet over here. So what is like happening here at small z? Yes, so yeah.
So are those the jets that don't carry the energy?
What do you mean by don't carry?
Like there's one jet that's likely to carry most of the energy, and then
right.
The other
Exactly. So, right. So they still carry some energy, right? They carry something that's just very small, right? Exactly. But since it's inclusive, right, we'll count all the energy, similar to hadrons, right? Like the fragmentation function. It's not, right? And the important thing is that these are not probability densities, right? They're not normalized to 1, right? They're all number densities. I'll get back to it a little bit later. So there's like different numbers of jets and hadrons that are produced in every single event, right? That's why it's not really normalized. But it's an inclusive quantity, and since it's inclusive, we not only count the leading jet, right? Leading jet would be anything above 0.5, right? That's automatically leading jet. But down here we have the second, the third, the fourth leading jet, whatever, right? They will all appear here. Okay. And so here we have this nice peak. Here we actually have a divergence. If we go to very small values of z, I'll say a few more things about this later, but it's usually just cut off by the integral, and so we don't really need to worry about it. We can worry about it. I'll say a few things about that later on. Okay, so we have 2 peaks, one at small values for all the softer stuff that is produced, and then there's one gigantic thing, right, that carries anything. And so that's basically this, right? You have a small sort of, it gets a little more blurry, right? Because you have this leading jet that matches exactly pretty much what the quark was, and then you have a little bit other stuff as well, right? And that's what makes this a little bit blurry, right? But the nice thing is we can actually quantify that, right? Like if you look at the quark distribution, the jet distribution, right? they're not exactly the same, but this function allows us to quantify why they're different, how different they are. Okay. Yeah.
And does that IR divergence come directly from the soft gluon IR divergence theory?
So I'll say a bit more about the divergence structure later, because we'll take a look at how to calculate this. This is I would say, collinear divergences, right? So you basically, also for fragmentation, right, you usually obtain like a collinear divergence. There's some details about how to exactly call them, but everything that we have here, there's no soft gluons in this factorization. They all have a one, say, dimensional regularization, right? They have a 1/epsilon pole. If you also had a collinear soft collinear singularity, it would be 1/epsilon squared pole, and they don't exist here in that particular factorization. There's some subtleties, so I'll get back to that a little bit later. So basically, whenever you're at the endpoints close to 1, or if you're close to 0, then that argument does not quite hold. But I'll say a bit more about that later. But here's basically, it's a similar collinear divergence as a fragmentation function or a PDF. So in that sense, it's very similar. The difference, though, maybe I should mention that, right? Like if I take these functions, right, there's no divergence left, right? So if I do a perturbative calculation and I observe a hadron in the final state, right, then I have a divergence, right, and I have to then introduce a fragmentation function to get rid of that divergence, right? Here, I'm not going to end up with a divergence, right, because it's infrared collinear safe. Infrared collinear safety makes sure that for that particular final state, I'm not left with any divergences. Okay, so that's like an important difference, and that's why I can just do the calculation perturbatively, and I don't have to introduce a fragmentation function that I have to extract from data. Okay, so that's sort of the important difference. Any other questions? And I will take a look at how to compute that. This is so this difference, the difference in sort of the fragmentation, right, of hadrons and jets. That's really the main point, and that sort of allows us to understand these differences and why jets are these good proxies for particle level dynamics. Okay, one more thing. Okay, this is not very important, but one thing is, of course, it depends on the jet radius, right? If I choose a very large radius, right, it's very likely I capture everything, right, and I get this this peak here at very large values of z, right? But if I choose a smaller radius, right, it's less likely that I capture everything that was initially available, and instead it will split up into multiple jets, right? And that depends on the algorithm, it depends on the jet radius, okay? So here I choose a jet radius of 0.7. That's like in units of distance, basically, right? So I mean, that's just one particular example. I think on the 2D plots, I showed before and yesterday, I think we had jet radius of 1, here's 0.7. And so what happens now if we use this jet radius, where we have this peak, then we can choose a different jet radius, where I say this is 0.5, this is 0.2. And so what you see is if you make the jet radius smaller, this peak disappears, right? Because if I would take the sort of the extreme limit of r going to 0, right, then I just recover hadrons, right? So if I take the limit formally to 0, right, then what I end up with is basically a fragmentation function. Of course, that transition would be non-perturbative, right? So I can't compute that directly. But we sort of see roughly what's going to happen, right? Like the peak is going to disappear slowly, and it's compensated for by an enhancement in the small z region, right? Which is all these softer, lower energy jets, right? That are also produced, or that we basically artificially split our jet into multiple jets. And if we split it into every jet is just a single hadron, then we have a fragmentation function, right? And you can sort of exactly see that happen. But if I make the radius smaller and smaller, this peak is completely gone, and I just get this rise here in small z, right? So then it's basically a fragmentation function. Okay. Does that make sense? Good. Okay, let's take a look at. Well, maybe just in case anyone is working on small x physics, this divergence here at small z is actually related to the BFKL equation, and there are additional logs, that are relevant in the small z region, and it's kind of the same thing as BFKL, but not too important.
Okay, so let's take a look at how to compute that, that function. So let's start at leading order.
At leading order, we just have this is a dashed line. It's just a port line. It's dashed because it's collinear, but it's not too important. So in leading order, we just have a single port, okay, and we're gonna measure the jet, right? So we draw a cone around it. Well, we draw a cone around it, but so what we're going to use is will be anti-KT algorithm specifically. But it's just a single parton, right? And so in this case, of course, the momentum fraction z that's contained in the cone relative to what was initially available is, of course, trivially 1, right? Obvious. And that's completely independent of the jet radius, and it's independent of the jet algorithm. Right? So at leading order, okay, now this is for the quark. This jet function is simply given by a delta function. Okay, it's just setting z equals 1. Right, that's the first order in when we do the perturbative calculation, right? And so if you look at this, right, numerically that would just mean we have a delta function sitting here exactly at 1. Right, that would be the leading order result. Because that's obviously kind of trivial. So we should at least look at one order higher. Okay, so at next to leading order, we have start again with the quark, and well, we know it can split into 2, right? That's at least what can happen. It can still, so there's two ways how, well, there's a virtual correction, and then these are real emission diagrams. Okay, so this is kind of similar to what we did for the Sturm-Weinberg algorithm, where we consider virtual correction, and then hopefully all the divergences again cancel between the different contributions. But now we basically have to think specifically about the kinematics of what happens if I have this 1-to-2 splitting, right? The quark splits into a quark and a gluon. And now it depends on the jet algorithm and the jet radius, whether they will be identified as a single jet. Right? So if the splitting happens such that the particles are close together after the splitting, then the jet will capture them, the jet algorithm will capture them and identify it as one jet. Right? And in that case, again, we have z equals 1, right? Similar to the leading order contribution. Okay. But if the splitting is like too far away, like if the two partons are too far away from each other, then we get the non-trivial dependence on z, right? It will not be 1 anymore. And since we're inclusive, we have to just sum over these different contributions, right? If the splitting is too far away, then we'll get 2 jets. We'll get quark jet, and we'll get a gluon jet, and we just have to count both of them. Okay. And so in this case, we then have to decide when does that happen, right? Like when do we transition? I should have reordered them a little bit. Like this one is trivial. One has to do the calculation of divergences, but like here, one has to basically distinguish: does this happen or does this happen, right? Are they in the same jet or are they in separate jets? And so that basically now depends for the anti-KT algorithm, right? That basically looks at distances between particles. Right, I basically have to decide, is the opening angle here between these two partons sufficiently small that they will be in one jet, or is it too large and they'll be in separate jets? And the way to do this calculation is to look at the momentum fraction and to look at the relative transverse momentum. So it is basically, so this splitting here in general, right, from 1 to 2, is governed by an Altorelli-Parisi splitting function. And that's, for example, for a quark to a quark glue final state, like shown here, or we do it for a gluon to 2 gluons, or gluon to a QQ bar. That's not shown here, but that's all captured in this. So we start with 1 parton, it splits into 2. These partons now have a transverse momentum here, QT, relative to the initial direction. And what we want to know is this opening angle here that I call beta here between partons J and K. Okay, that's the opening angle that we need to look at to decide whether the jet algorithm will put it into 1 or 2 jets. Okay, and so basically, when this angle is less than the jet radius r, then it will be a single jet. If it's larger than r, it will be 2 jets. And one can work out the kinematics by basically in terms of z and transverse momentum qt. Then this angle beta here is given by this expression here. Okay.
Okay. And yes.
So is R defined in terms of the angular radius?
Angular radius.
I just want to know how you're trying the units of beta and R. It looks like an angle. Radius usually is a distance.
So, oh, I see what I mean. Yes, I skipped here something for simplicity. How can I? Yes, there's an approximation that you're making, but I unfortunately don't have this in the slides, where you're basically relating like the distance, like in the eta phi plane, to an angle, and what you're allowed to make, and that I didn't comment on that, is that this holds up to power corrections that are suppressed in powers of the jet radius. So it formally holds this equivalence if R is sufficiently small, but it has corrections that are generally of order R squared and R to the power 4. These corrections are generally found to be, like, we actually don't know what they are analytically. That's one of the open questions. No one has made the effort to compute them. But from comparing to experiment, we always find that they're extremely small. There was other ways to do it, but like for anything that we know, these power corrections are very small. And in that case, I can make that connection up to order R squared. And that's actually also here, this factorization here holds up to powers of order R squared and up to power corrections of order 1 over PT. So here for jets, we generally have 2 expansions. One is always in the jet radius and one is in, say, at the hard scale. And for hadrons, you only have the hard scale, not the jet radius. So there's 2 expansions. And so if we make this expansion, and there's like a short calculation to show why one is allowed to do that. One can sort of make this comparison of angles and relate it to R, which I can look up. But yeah, there's an additional step in there that I'm skipping.
Is there anything that changes with the normal KT algorithm or the other one? There is
Yes.
no mean.
Yes, exactly. So at this order, the anti-KT, KT, and Cambridge-Aachen are the same at leading power. So they will be different at order R squared, and they will be different at next to next leading order, even at leading power. But here, it's purely an angular constraint on the 2 particles. Exactly. That is a simplification that works here. It doesn't work in general. That's right. But exactly, that's why, yeah, that's a good point. Right, all the stuff that I discussed before about, whether there's in the distance metric Dij, if there's a KT squared or 1 over KT squared or no KT at all, that doesn't matter at next to leading order at leading power. But it does matter in a lot of other cases. Right. So for example, if you look at substructure, then that will matter more. Here we're just interested basically. But so what we're measuring here is really just the momentum fraction Z that's contained in the jet, and that's a relatively simple thing to do. In general, that will be, one has to worry about that. Are there any other questions? No? Okay. So let's take a look at how we can actually compute this. And this is a little short to really like understand, the details. But yes, you can look at this reference here, where this was calculated in quite some detail. And there was other references that a little earlier that didn't look at inclusive jet production, but other jet production. And so if you have questions and it's not clear how to do the calculation, just ask me. I can give you some more details. So the way we do the calculation now of this jet function, right? So we saw it trying to do the analog calculation, is that we have a matrix element squared, right? We have some phase space and we need to integrate it and we need to do a measurement, right? That's always how we do any calculation, right? We square, in this case, the collinear matrix element. We integrate out the phase space, and then we have to put in a measurement. The measurement here is just the momentum fraction contained in the jet. But if we wanted to ask more questions like, what's the jet mass, for example, then we can put that in as well. Right? So this is the general expression here. So we have some integral over the phase space.
Then we have the collinear matrix element here that's written as sigma 2 specifically for a quark, and it's the collinear approximation, right? So that's why it's basically based on the D-Lab splitting function here. So that's just the matrix element squared. And then we have the constraints from the jet algorithm. The constraints for the jet algorithm are given here. Okay. And so here now, this is the result in dimensional regularization. I didn't derive that in detail here. But if you're interested in where exactly this is coming from, then just let me know. So we have a bunch of prefactors here that basically just make sure everything's well-defined dimensional regularization. There's an overall alpha S over pi, right? Because we have one emission, so we have a quark emitting a gluon. So overall, well, everything squared, right? We'll get one alpha S. Then we have an integral here, so basically parameterize the phase space of the emission in terms of the momentum fraction z, so that's the Coulomb momentum fraction carried by the emitted gluon or quark, one or the other, and in terms of the transverse momentum. So it's basically these two variables that characterize the phase space of the emission, and this is the matrix element squared. That's in this case, it's just for example, right, so the splitting function, and here it's specifically the quark-quark alternating Parisi splitting function. Okay, but this is what we know is from like D-Lab evolution, right, of PDFs that also has this as an evolution kernel, right? There will be exponentiated. Here we'll later also exponentiate this, but for the fixed order calculation, that's basically the matrix element squared. Okay, so this is what's written here. And then we still have an integral over Qt, right? That's also very similar to what we had in the Sturman-Weinberg algorithms, right? There we had 1 over the energy, 1 over the angle, and then, luckily because of the way the algorithm was chosen, it cut off the singularities. Here we also have now 1 over Qt. Here we also have basically something like that, right? We have dz over 1 minus z, so that's sort of the analogous version. Okay? That's basically what where you can run into divergences, right? And so here we now use dimensional regularization, and so what happens is that it's not just 1 over Qt, but it has a plus 2 epsilon. And so that basically just makes sure that if the divergence is coming out, right, at the intermediate stages of the calculation, they will all be regulated. So that's the nice thing about dimensional regularization here, anything like gauge invariance, whatever we might worry about with, for example, using a massive gluon to regulate things, that's all taken care of, right? We can always use dimensional regularization. Okay, and so then basically what we need to do is we have to put in here at the very end, right? We want to measure the momentum fraction, and we basically put in here this constraint, right? So if it's just a single jet, then we'll again get out the delta function, 1 minus z times the prefactor. Or if they're in 2 separate jets, we'll get some non-trivial functional dependence on z, right? And so this constraint basically will go in here into the jet algorithm constraint, and then we basically just have to perform the integrals. Okay. Let's see. Okay, so this is still an illustration of sort of phase space region, right? If I take this and I write Qt in terms of z and 1 minus z, then I get this kind of, right? This is z 1 minus z, but that's x between 0 and 1. And so whenever my transverse momentum is too large in this like out region, right, then I'll get 2 separate jets. And if it's sufficiently small, then I'll get 1 jet. Okay. That's basically what I'm getting here, this Qt integral. And so let me just show you what the result is. Here's the next leading order result, right? So we have up to next leading order. So we have again the leading order contribution, right? The delta function at z equals 1. Then we have now a term that's alpha s over 2 pi, right? So everything here is the next leading order calculation. We have a logarithm here that comes with some scale mu divided by the height. So that's the hard scale q times the jet radius. Then we have additional logs like a small z log, a log in the threshold variable z, when that becomes relevant and z is close to 1. This becomes relevant when z is close to 0. This is multiplied now by the alternating Parisi splitting function. it's multiplied by both the quark splitting function and the quark to gluon splitting function, right? Because we're inclusive. If we have a splitting and we multiply it by, and we identify jets, we have both a quark and a gluon jet. So we have both the splitting functions here. That's the inclusive aspect of this. And all of this, right, it has like a finite or a non-trivial functional dependence on z, right? So whenever you see a z dependence, that is not a delta function. So here we have a delta function term that comes from, when they're in the same jet or from the virtual contribution, right? Then we have a delta function, but everything else is basically coming from the real contribution when the two jets, when the two partons are not in the same jet. Okay. So, all right. So if you have, yes, go ahead.
Could you speak a little bit more about the P?
The say again?
The P.
The P, yes. So that's the splitting function, or the ultimately Parisi splitting function. It's basically similar to this, right? So this is the quark splitting function. In dimensional regularization, you get this additional term, but like on the next slide, it's basically just this first part here, the 1 plus z squared divided by 1 minus z and overall cf. That's the splitting function, right? That's basically what you also have as in DGLAB evolution, right? You get exactly that PQQ that evolves to PDFs, right? Or that's the evolution kernel. And so here we have a sum over both. Like the other one, the quark splitting function is basically this, and the quark to gluon splitting function is the same, but you switch out z with 1 minus z. And then you get 1 plus 1 minus z squared divided by z. That's the quark to gluon splitting function. And so, what you find here is that, especially this term, and I'll say more about, this term in particular on the next slides, or about the different terms. But you find that, in particular, this term here is multiplied by these two splitting functions. Okay, and that's basically what's going to give you, as I said, like this, what we mentioned before, these functions will evolve according to DGLAB evolution. And so what I mean by that is if you take the log derivative of this function, right, so take derivative with respect to this, then what you're basically left with is the splitting function. And that's exactly what DGLAB is, right? If I take the log derivative of normally a fragmentation function, then what I'm getting is a convolution of the ultimately Parisi splitting functions with the fragmentation function. Okay. And that's exactly what this is going to lead to. Does that answer the question? I'll say a bit more about the details on the next slides. Yeah.
Where the new scale comes from? It was not in the previous formula, and
so
it's supposed to be infrared state. Oh, okay. And where does that come from?
Oh, this is coming from. And this is coming from dimensional regularization. It's basically just making sure that you have an additional scale with, to the power of epsilon, right? To make sure, right? Because otherwise I wouldn't have, like otherwise I would have like issues with the dimensions here, right? But that's really just an aspect of DIMREG, right? Otherwise, I would.
Because it's not a renormalization scale in the sense that you don't.
It's a renormalization
scale.
It's
not a factorization scale because it's infrared safe, so you don't have to.
So let me see what I have on the next slide. Yeah, so yeah, maybe I should have put a few more details here. So yeah. So I guess I skipped here a little bit. So in principle, there is a divergence here as well, 1 over epsilon divergence that's associated with that scale. I just removed that. So it's basically the renormalized jet function already. But you can derive it, but it will get on a renormalization group equation that is DGLAB. And you can either derive it by just doing the renormalization of the function. So you first include the divergence and then renormalize it. That will give you the equation, or you basically just directly take the log derivative with respect to mu, and then you also get DGLAB. So that's why I sort of took a shortcut here. So of course the question is, why is there still a divergence? Why is that was just skipping that part. So the reason that there's a divergence, even though I said it's infrared collinear safe, is I'm using
basically here an artificial, or well, not artificial, but I'm using a separation here between the hard function and the jet function. And if I didn't do that, right, if I would just group them together, then there would be no divergence left. But now I'm basically artificially separating the two. And there's a reason why I'm separating that, which I'll get to on the next slide. But if I didn't do that, then there would be no divergence. And so now I artificially separate them, and then I'm introducing a divergence, and the divergence leads to the dependence on the scale mu, and it will lead to a renormalization group equation. And so that's basically now DGLAB. So we have here the dependence on mu divided by q times r. And so this log here is something that you could worry about, right? That's similar to Sturm and Weinberg algorithm, right, where you had a log in epsilon and delta, right? Like that algorithm was dependent on two parameters, epsilon and delta. This algorithm will only depend on one parameter, which is r. Okay, but that's basically the same thing, right? Like in the other case, we had this double log term, right, that I talked about. It was a log in epsilon times a log in delta that I talked about yesterday. Here, there's no double log. It's just a single log, right? It's just a single log in the jet radius, right? But it's very similar, right? If I choose epsilon and delta to be very small, but the jets are very narrow, or if I would have a very strong constraint, the outer jet radiation for Sturm and Weinberg, then I have a problem, right? Then the logs will be very large, and alpha s times the log will be an order one quantity, right? And so if that becomes an order one quantity, then I have to worry about the n and alone contribution, the next leading order calculation, and it gets very difficult to actually do that. Okay, and so what I can do, I can just pick the scale here. Well, so first I get my renormalization group equation. Let's do that first. So if I take here the log derivative of the jet function, then I'm going to get alpha s over 2 pi, right? Alpha s over 2 pi. This is the log derivative, right? So that's what I want to take derivative. I'll take the derivative with respect to that. And then what I'm going to left with is just here the ultra-rally Parisi splitting functions for quarks and quarks to gluon. Okay. And then I basically, so I get the right-hand side of this, right? I get the quark and the quark gluon splitting function. And that will be convolved at this order, it's trivial, like this at leading order is just a delta function, right? So I'll basically just get the ultra-rally Parisi splitting function. Okay, so from this equation up here, I can read off generally that this will follow this evolution equation. Okay, and that's really the same as for a fragmentation function, right? If I did the calculation for a fragmentation function, I would get the exact same evolution equation. Okay, and now the question is, again, if we have a PDF or a fragmentation function, right? I'm basically resumming logs, right? By solving DGLAB evolution, right, between two different scales, right? If I didn't do that, right, I would have large logs in my perturbative calculation that would completely invalidate it, right? And so the question is, what are the logs here that are being resummed, and what is resummed are logs in the jet radius. So the hard scale, so there's two functions, right? In the factorization, there's a hard function where the characteristic scale is the hard scale q, and here the characteristic scale is q times r. So what I can do now, if I have this fixed order expression, I can just choose mu to be q times r, and then this entire log will disappear at fixed order. And then I solve my evolution equation. So the DGLAB evolution, I take that as a starting scale, and I evolve up to the hard scale q. Okay, and by doing that, what I'm resumming are logs in the ratio of the two scales. The ratio of the two scales, of course, just r. And so what I'm doing is I'm resumming logs in the jet radius r. And then I basically put that into my factorization theorem, right, that I have here. So I had two PDFs, the hard function, which sits at the scale q, and I have a jet function that I integrated, against each other that sits at the jet scale q times the jet radius. And so by doing that, I've resummed that particular log, right? And so that's, there are like details on how to do that technically, but it's really the same thing as if what you would do for solving the evolution equation for a PDF or a fragmentation function. But the logs that you're resumming here is different, right? It's related specifically to the jet radius. But you can sort of see why that makes sense, right? Because if I now again take the limit of R to 0, right, then this will basically become a non-perturbative scale, and then I again have a fragmentation function, right, where I would basically also evolve, say, from 1 GeV up to the hard scale. Now, if I take the radius to 0, right, every jet has just a single hadron in it, then I recover here again the structure of the fragmentation function. So there are technical details to this. So if you have any questions, either now or also later today or the week, feel free to ask me. I'm happy to explain them or send you some references on how to do the calculation. So the main idea is to sort of give a little bit of an idea of how generally one does these kind of calculations. There's a little bit of sort of magic in it that is basically related to soft coin effective theory. The reason I'm allowed to do all these different things may not be immediately obvious if I think about it sort of from a direct perturbative QCD way, but they all work out nicely in soft coin effective theory, but that would go a little bit too far. So I'm sort of trying to skip the details, but if you're interested, I'm happy to send you details or explain them in more detail. But it's sort of a very general idea. Like in all of jet physics, what you're going to do, whatever observable you look at, you could in principle combine functions together, but then this would contain a large log in the jet radius, right? And if the jet radius is small, we don't want that. So what we do is we separate the two functions. There will be a scale separation between the two functions. Here it's a scale separation in terms of the hard scale and the hard scale times R. Then we solve the evolution equation, and that will effectively resum it, right? So we do a factorization, and then that allows us to do a resummation. So it's very similar to what do you do for hadron production or for PDFs, except that here now we're talking about a jet. Yeah. Are there any questions? I'm sure it was a little bit too quick, but if I can try to clarify anything, please let me know. Yes.
That's kind of a big picture question. So depending on like how you define your jets and what parameters you use in those definitions, you can come up with very different sets of like, here's what the jets are and here's what particles are involved in that. So does this lead to large systematic errors in your physics results?
So it will be included here in these calculations, right? So for example, if I would use a Kona algorithm, then I would get a completely different function. And so I would get different constants here, but I will also get, there will be some theta functions in terms of Z. Like basically what changes for cone, for example, is this integration region changes. Here we have kind of this circle, mostly because we're looking at pairwise distances. First of all, the cone, we basically look at the distance to the cone or the center of the cone. And this basically becomes kind of a triangle in the integration. And so one basically just has to take that into account in the calculation. Right? Like if the experimental measurement done is in a different way, then one has to adjust the calculation to do it. And it sort of depends on the observable. If we're just, this is sort of the simplest case, right? If we think about jets, it will just depend on Z. There's no other observable, right? These are just scales, right? The only observable we have here is Z. If you now ask more differential questions, for example, so they would still depend on Z, right? Other jet functions, but they would, for example, also depend on the jet mass and things like that. And then, then it will be more sensitive to how I actually identified the jet. And I just have to take that into account. So I wouldn't say it's like an uncertainty, right? It's just that one has to just match, what is done in experiment. And that sort of is also why this has, been taking quite some time. And it's sort of a joint effort between, the theory and experimental community, primarily coming out of the LHC, but also, Rick and so on. Where people have been trying to understand like what can be done experimentally very well and what can be done, on the theory side very well, and where can you sort of find overlap, right? Because initially these things were very different, right? We could, for example, very easily compute the jet mass, but then it just turned out to be very difficult to treat that. No, sorry, we could measure very well the jet mass, but it was very difficult to treat that theoretically. And so then there was sort of a joint effort to sort of bring these things together. And so here it's it's fine. I'll have I think I have a comparison to data on one of the next slides. So this just works generally very well. But if you do something different, experiment just has to account for it on the theory side as well. Any other questions? Yeah. Sorry, so the plots.
The plus,
This one. Oh, plus distribution. Oh, sorry. Yes, right. So right, I was going to comment on those. Exactly. So what you see here is actually, right, this is like one type of log, right? But there's two more. And so one, let's say one can worry about them. The reason one doesn't have to worry about it in this particular case is that it's integrated against a hard function, right? So if you look at this previous slide at the bottom right, it's part of a convolution integral against sort of everything else in the cross section. And that convolution integral starts from a lower bound. I don't have the formula, but it's something that depends on PT and rapidity of the jet and a center mass energy. So it's somewhere, it's like not zero, right? It has like some upper value, right? Something. So it's an integral, not exactly. Okay, so the allowed range we see is generally between 0 and 1, but there's a lower cut, right? So it doesn't go down to 0 exactly, but does go up to 1, right? And so if it goes up to 1, you could worry about this one. And if you go to very low PT, right, that this lower bound on the integral goes close to 0, then you also may want to worry about this one here. This one, so now they're both known how to treat them. But so the way you do the, for example, sketch calculation, right, is or soft effective theory calculation is that you choose the scale that removes this log, right? So this log will disappear, they will remain. And so the way you can, if you want to worry about those, right, and also make sure that they're somehow not existent anymore at fixed order, but that you resum them, right, that you account for them to all orders in perturbation theory, what you have to do is to further factorize that cross section. Right. So here we basically factorize the cross section into two functions. If you want to factorize this one as well, you have to introduce two additional functions. And then you have each function depends on a particular scale. And that allows you to resum the threshold log as well. So it's again like sort of the same idea, right? That you write down multiple functions, each function depends, right? This is the problem of this function is that it just leaves these two logs, these other logs over, right? That's the problem. So you can further factorize this so that each function really just has a single log, and then you can remove it at fixed order. You solve the renormalization group equation and will be exponentiated and therefore take into account to all orders. So for that, this result is not sufficient, but you can definitely account for this one. This one is a little bit more tricky. There we actually don't know how to do it in soft Klein effective theory. That's a much more difficult log to deal with. But so there's two logs. So one is a single log series. So let's forget the small z log for now, but there's a single logarithmic series in R, right, that we can directly resum here with Diegler. Then there's a double logarithmic series. So for every power in alpha s, we get two logs in 1 minus z. And that becomes relevant whenever, in this plot, we're close to values of 1. Okay. And so maybe I should still mention that the plus here, right? That's basically just making sure that we can integrate it against the hard function. That basically, I'm not sure if you guys are familiar with the plus in general, but it basically just means that if I don't have the definition, unfortunately, in slides, but it basically just makes sure that it's integrable. And that it's not divergent, even if I integrate it to 1. So what happens? Can I write somewhere?
Yeah.
Okay, thanks. So if I have some integral of some function from 0 to 1, right, then I worry about this endpoint here, right, when z becomes 1. And so if I don't have a plus here, then I can't do this in general. But with a plus, or what that implicitly means is that whenever I integrate a function with a plus against such a test function,
this function here in this case is basically, oh, disappear. That's the hard function over here, right? It's sort of everything else, right, of the cross section. And so if I do that, then what I'm getting implicitly with a plus is one minus z, right? And so that basically means, like, as long as this is like smooth with z going to 1, right, this will basically just be 0 at the end point. Like this and something is like integrable as long as the function f is okay. Right? And it turns out the f is okay here. If it were not, that'd be okay. So that's implicitly what is meant by the plus. So it's like integrable. You don't have a plus here, right? Because we don't actually integrate this to 0. What we're actually doing is we have some lower bound, something like this. Right? There's some 1, 0 lower bound. So I don't need a plus for the z equals 0, but I need a plus for the z equals 1. Okay? And these terms, they become relevant, and actually they are included here. So the threshold logs here are included here in the plots that I showed you. They're relevant here close to 1. They basically are what gives us this nice peak structure here. If I didn't include those logs correctly, they would just be divergent, right? Because this will basically make sure that an integral over the function is finite, but the function itself is divergent still, right? If I just plot it as it is, right? So if I would just plot the next to leading order here, then I would just get a divergence here, right? And so what I did here to make it look nicer is actually include the threshold resummation also in the numerical results. Mostly just because it's nicer to look at. Or it gives a more physical interpretation. But yeah, so that basically does a joint resummation of the single logs in R and the double logs in the threshold, and this is sort of a separate question. But yeah, good point. Any other questions?
What about the second power of the log up here from? I read only one power of the log.
So
There is only one log, not a log square in your box.
Oh, you mean why this is a log square? Oh, I see. So yeah, so if you go to one order higher, it would be log cubed. So for every additional point alpha s, you'll get 2 more. And the way so yeah, this is basically, I think of the cumulant here, right? You will get a double log or already an analog if you integrate that thing from 0 up to the upper bound. And then, or if you go to a Mellin space, right, that will give you a log in n, a log squared in n, and then a Mellin variable n. And then it's sort of more obvious that every additional power will give you 2 more logs. So yeah, that's not obvious. That's right. But I just thought it's like simpler to write to n in general. I mean, they're like also this one, right? Like it's similar. It's the initial, right? Like this, you can always have a double log counting at some point, but it may start at a higher order, right? They can also be, in general, right? They can be logs in a fixed order calculation that don't show up at NLO, but they will still be double logarithmic starting, just 1 order higher, right? That so that the starting point of the log counting can be off by anything. Yeah. Okay. Other questions? How are we doing about time?
I think we have 5 more minutes.
Okay, 5 more minutes. That's great. Yeah. Maybe if I can have just a few more minutes, then I'll come to a good point to end this, and then we'll do the machine learning tomorrow. So what I still wanted to show is some phenomenology, right? And so what the experiment measured here that was historically very difficult to compare to is a ratio of inclusive jet cross sections for different values of the jet radius, right? So that's basically what this function tells us, right? Like if I measure jets with 0.7, how does it change when I go to 0.2? Okay, so that's what they try to measure. And right, sort of normalized
the cross section with a particular radius, and then you just vary the radius. And it's a little bit difficult to see, unfortunately, but this is the ratio of theory calculations to the data. Right? So ideally should be at 1. And then it's plotted here as a function of the jet radius. Right? So it's normalized by 0.4. So that's why here at 0.4, everything is okay, right? This radius is just 1. And so then what you see here are different theory calculations. And so what you see here in black is what happens if you just do a fixed order calculation. Let me see. Oh yeah, sorry. This one. This is like this is like a fixed order calculation, right? So that's what I mentioned before, like the calculations like from the 90s, right? If you just do a purely fixed order calculation, right, then and you take a look at the ratio to the data, then you see that you're quite a bit off, right? You don't correctly predict the dependence on the jet radius, right? But now, if you use what I just talked about with these jet functions, right, and where we're summing the logs in R, then that's a little difficult to see, but the calculation is shown here in orange, right? It matches perfectly. That's the main point. So what it's just telling us is that in this case already, right, even if R is not particularly large, sorry, not particularly small, right, that I would think, you know, like a log of 0.6 or so is not necessarily very large, right, that I would have to worry about that necessarily at fixed order, right? But it turns out that you do have to worry about it. So that's kind of like an odd thing of QCD, I think, in general. Like very often it's very difficult to sort of make parametric arguments and say, well, you know, like an R value of, you know, even 1, right, is that large or small, right? Or say 0.4, right? Is that a log you should worry about or not, right? In the end, you can only really determine that by looking at data, right? By doing the calculation and checking if it works or not, right? So it's very difficult often to say, is it right out of these logs, you know, that you see here, is this something you should worry about in the fixed order calculation, right, when it's multiplied by alpha s, or is this one problematic, right? And so it turns out this one is actually the one that you have to really worry about. This one is not that important. And that's kind of a weird thing of QCD that, you know, you don't know until you actually give it a try. And so the main point of this is, well, that one, you know, thinking about it in terms of jet functions as opposed to fixed order calculations gives us a very intuitive way to think about jets, right? But if we think about it as this function or this universal function that tells us how we go from quarks and gluons to jets, and also, you know, it just is necessary to describe the data. It's necessary at the LHC, right? We're here at 13 TeV, right? And we're looking here at jets of 500 GeV, right? It's really high energies. So alpha s is small. If we go to EIC energies, will be much lower energies. Alpha s will be larger, and we then really have to make sure that we use the correct framework, right? Where these type of effects will generally be more important. And maybe one last comment about this inclusiveness that I mentioned, right? These jet functions, and in general, you know, these jet cross sections are not probability distributions, right? But instead, they're number densities. And at the jet function level, that basically means if I integrate this function, right, then I'm not getting 1, right? So it's not a normalized probability distribution, but I'm just getting some average number of jets, and they're different in every event, right? But what is conserved, or like, you know, how I can get that integral to be 1 is if I multiply by z first, and then, you know, I get 1. So it's not a probability distribution, but the momentum is conserved, and that basically just means if I say start with a quark, and I have a bunch of emissions, right, that are captured by exactly that jet function, then if I add up all of them, right, the momentum that's contained in all the 3 jets, right, that has to add up to 1. So like if I add up Z1, Z2, Z3, whatever they are, right, then I always have to recover 1. So that is, it's like there's momentum conservation similar to fragmentation functions. But also, like if I take fragmentation functions, right, and I just integrate them from 0 to 1, I'm not getting 1, right? So that's like an important point. Like if that we're not dealing with probability distributions, but always number densities for these inclusive quantities, and that's sort of you know, what one can check explicitly here. I think yeah, I think I'll end here. And Are there any questions? Okay. Otherwise,
Can you go back to the previous slide? Did it say anything about the positivity of the jet function?
so yeah, so right, so you can make it a probability distribution if you don't make it inclusive. So if you take only the leading jet in the event as opposed to all of them, then you can make it positive. And you can make it positive. So one, you can normalize it, right? So here we always get different number of jets, right? We have the event average and we'll get like some number, right? Also here, right, like if you just try to take the integral, right, then you have like the logs in z, right, that are going to be a problem, right? So you have to first resum them, then you can do the integral. But you can make it a probability distribution if you just take the leading jet, right? That's why it's like a curly j as opposed to normal j. And if you do that, right, then you can make it be normalized to 1. But then you really just can always take the leading jet, and that can be sort of difficult for other reasons. And you also want to make sure it's right to really interpret it as a probability distribution. You have to also make sure that's positive. And that's not generally the case. So if you do like a fixed order computation, it's not guaranteed to be positive. And so what you find is that you have to worry about these endpoints. So what can happen if you don't do the threshold resummation, these, right, because this is not, at this point, it's not a cross section, right? It's just part of a cross section that you have to integrate against the hard function. So if you don't do the threshold resummation, those things can become negative. And then you again don't have a probability distribution that is, I mean, like probability is like positive and normalized to 1, right? So it's normalized to always normalized to 1 for leading jets, but you have issues potentially with the positivity if you don't resum all the logs that you need to resum. Does that make sense? I mean, so they're also, right, so maybe one comment related to this, right here, where did I show this? Here, for example, right? So, right, this is the cross section for inclusive jet production, right? It just falls off very steeply toward 1, right? Versus the jet functions I just talked about, they have a peak at large values of z, right? But there's no peak here, right? It's very unlikely you find jets with that high PT, right? And the reason is just the hard function, right? The hard functions falls off very steeply, right? If you integrate it. Even though this peaks at large values of z, this clearly doesn't, right? And this is going to win over. But you can construct cross sections where you see the peak structure of the peak explicitly in the cross section, right? Because here's more like a mathematical tool, right? To actually do the computation for the cross section, it falls off very steeply. But in E plus C minus, or like there are other ways to do actual cross section where you see like peak structure. And then, that definitely has to be positive, because that's a cross section, that's not a mathematical part of a factorization, and then that will definitely be positive. So you can, for example, at the EIC, right, you can measure these type of things, right, that actually peak at large values of Z for jets. So you just have to change the measurement a bit. At the LHC, it works as jet substructure, but not directly. Right. But yeah, so there are differences between, cross-section level and part of the factorization, where things can be negative. Right? It's not guaranteed. Any other questions?
No questions. Yes.
It's a nice question.
Sure.
These jet functions are functions, so when they harmonize software at some point.
So can
Can they harmonize at some point, or you can measure it?
So, right, so they're purely perturbative, but of course, if you do a measurement, right, it's done on hadrons, right? And so generally what you then sort of invoke is like partial hadron reality, right? That if you're expressing your energies, it's okay to do a partial level calculation without having to worry about hadronization.
So it should match really one-to-one. But I mean, you still have non-perturbative components in the PDF, right? But you have no non-perturbative part here, right? If there's no fragmentation function or something like that, right? And it turns out that's totally fine if you're just interested in the jet PT cross section, right? The one I just showed, right? That just falls up very steeply, then you don't really need hadronization corrections. But if you ask the question about like the jet mass, for example, then you need it. Maybe I can just quickly show that. We'll briefly cover that tomorrow, but like this is the jet mass distribution for LHC jets, and if you don't account for hadronization, you get this yellow curve here. So what it's showing is just a cross section as a function of the jet mass, right? It's like from 0 to say 200 GeV, right? It peaks at some value, right? And you can see that this yellow curve is like far away from the data turn and black. And so the difference here, and it's sort of counted here with a model, right, where you basically shift your purely perturbative calculation, and you try to account for hadronization in some average way. Then you can like describe the data, but the difference between yellow and red is basically all hadronization. And there are a bunch of other things that also contribute. And so in that case, it's not sufficient to just do a gluon level calculation and hope that will retrieve the data. That's sort of been one of the main issues, but if you look at these kind of deliverables, then you're really far away, and it's often very difficult. But like, even if you can account for it, right, somehow, right, you kind of, most of the cross section here is actually non-perturbative, right, and that's not really what you want. But so in some cases, one has to worry about it, and there's like ways to get rid of that contribution and so on. But so then it really sort of depends on observable by observable basis, right? If hadronization plays an important role, then one has to worry about that and think about how one can systematically include that. Does that answer the question? Okay, thanks.
One more.
From the chat. You're so quiet.
Yeah, anybody from Zoom? You can throw ideas in the chat. Carol is reading them. So maybe for the future. Okay, then well, you're quieter than the first week, but you are warming up, so I'm very happy. So don't hesitate to even ask more questions. So I would thank Felix again first. One more thing. Felix, what day are you driving back?
Still be here the whole week.
The whole week?
Yeah.
Okay, so he's here the whole week. There is no time and occasion to talk to him. I would suggest, maybe if you want, two possibilities. One is to meet this afternoon after 5 with also Anselm at 5, maybe as a recitation as we did online virtually before, but we can come back in person and discuss whatever. You want to do a little calculation, some of the things that is skipped, we can do that. Or we discuss about other physics, normal questions, anything else, soccer, Italy, Germany today.
Really? I have no idea.
Italy versus Germany today, or whatever you want. So one possibility is today at 5 or tomorrow at 5. Is anybody up for today at 5, you think? You can decide also later. So you can think about it and let us know later about what you would like. But we can have these two times set aside so we can do this. But otherwise, here you can get him on Slack and you can find him if he's not in the room. You can still get a hold of him. Okay, then we can break here.